In this video, we will begin by looking at the stereochemistry of 1R2S4S trichlorocyclohexane. To place the chlorines on the molecule, we needed to determine the configuration on carbon 1, 2, and 4 by assigning priority. To assign configuration for carbon 1, we began by putting chlorine on one of the carbon bonds. Now we need to look at what the stereocenter of carbon 1 is all connected to. Carbon 1 is connected to a hydrogen, a chlorine, carbon 2, and carbon 6. We then face the atom with the lowest priority to the back. Atoms with lower atomic numbers have lower priority. Therefore, in this case, hydrogen has the lowest priority. Chlorine has the highest atomic number and therefore has the highest priority. To determine the priority of the two carbons, you must look at what else those carbons are connected to. Carbon 6 is attached to one carbon and two hydrogens, whereas carbon 2 is attached to one chlorine, one carbon, and one hydrogen. Therefore, carbon 2 has higher priority than carbon 6, as chlorine has a higher priority than carbon. When drawing a circle from highest priority to lower, the circle should be drawn clockwise, resulting in an R configuration. If it was drawn counterclockwise, that stereocenter has S configuration, and therefore you need to move the chlorine atom to the other carbon bond. This process was repeated to decide placement of the rest of the chlorine atoms on carbon 2 and carbon 4 as well.
There are two energy conformations for 1R2S4S trichlorocyclohexane, one in its highest energy conformation and one in its lowest. To demonstrate, models of each energy state have been made. The highest energy conformation is seen in this model where chlorine is being represented as red. This is the highest energy state because the red chlorine atoms are the largest groups and two of them are in axial positions. This causes steric strain, which occurs when large groups are close enough to come in contact with one another. The lowest energy conformation is shown in this model where chlorine is represented as white. Here, only one of the chlorine atoms is in the axial position and two of them are in equatorial positions. This reduces the possibility of steric strain as the equatorial positions give the large atom groups more space and they are distanced from the other large groups. These two molecules are identical and have just undergone a ring flip. The molecule has the ability to change energy conformations with the ring flip. However, since the model with white has the lowest energy conformation and is therefore the most stable, this is the conformation that the molecule spends the most time in. For the highest energy conformation, these two chlorine atoms are axial and this one is equatorial. All three are cis to one another as they are all positioned upwards. For the lower energy conformation, this chlorine is in an axial position and these two are equatorial. Again, all three are cis because they are all positioned upwards. If the groups were all on lower bonds, they would also be cis. If two groups were located opposing each other, one on an upper bond and one on a lower bond, these groups would be considered trans. When looking at the cis and trans conformations of two atom groups, always compare groups attached to two separate atoms.
We are now going to explore 1S, 2R, 4R trichlorocyclohexane. This molecule has the chlorine atoms represented as green. When this molecule is in its lowest energy state, it is an enantiomer to the previous molecule 1R, 2S, 4S trichlorocyclohexane, when it is also in its lowest energy state. Enantiomers are two stereoisomers that are non-superimposable but are mirror images of each other. All the stereocenters, in this case at carbon 1, carbon 2, and carbon 4, have opposite absolute configurations of one another.
A meso compound is defined as a molecule that possesses a line of symmetry. Neither of these compounds can be considered meso because they do not allow for a line of symmetry to exist anywhere in either molecule.